As you may have learned back in grade 11, EK is equal to 1/2 mv squared. Of course, this formula here works well only if you're traveling very, very slow. All right, very slow is how we travel at relative to the speed of light, so this formula works very well in those cases. However, as you get closer and closer to the speed of light, even at 1% of the speed of light, this formula will not work anymore. So let's discuss about that. First off, this formula we covered from last class. This is your rest energy, and it's how much energy you have in you if you're able to completely remove all your mass. So if you are able to annihilate your mass completely, that's how much energy you got in you. Also, your mass changes depending upon how fast you're traveling. Here is your rest mass, and here is your relativistic mass. So if you take these two equations and equate them together, then you end up getting this formula over here. All right, and this is the total energy that you have of you moving and the mass that's in you. All right, so then the kinetic energy that you have while you're moving, well, that's the difference between the total energy versus your rest energy. All right, so this is our new formula here. As I mentioned from before, with regards to your momentum, you shouldn't expect your momentum to linearly increase as you travel faster and faster and faster. Your momentum gets out of control as you approach the speed of light. In fact, the same thing happens with kinetic energy. All right, initially, things move well, but when you get really close to the speed of light, the values just increase out of proportion. So let's go through a sample calculation for this. All right, what's the relativistic kinetic energy of an electron that's traveling at 9/10 the speed of light? So first thing we need to do is that we need to go and take this formula here and bring it all the way down. We're going to replace E total with this formula here, and we're going to replace E rest with this formula over here. We then sub in all the values, calculate it all away, and eventually we'll get to a number. And you can either measure it in joules or in mega electron volts. And that's the thing. Electrons, they require a ton of energy to move them that fast. Keeping in mind that one electron only possesses 1.602 times 10 to the negative 19 joules of energy. All right, so when you travel really fast, you can see how the numbers just get out of control. All right. Now, you might not be used to seeing this formula, and it looks really scary, but you're used to seeing this one over here. So through lots and lots of math, you can simplify it down to what you see back in grade 11. Now, for those that are curious on how would you derive that out, here's a lovely page where you can pause the screen and read through it. However, part of the solution requires you to know a bit about math and binomial expansion, where when you take a look at the stuff that's, I believe, inside over here, it can be simplified down, right? So you can clean up the formula quite a bit to get to your 1/2 ratio, all right? So there is a mathematical proof for this stuff here. As a reminder, electrons cannot travel at the speed of light, because if they did, wow, it's going to go crazy. All right, let's go through this example. Let's say you have one of those simple 5-watt chargers. The ones that came with the original iPhones and the iPads, which took pretty much forever to recharge. Well, even at a paltry 1 ampere or a 5-watt charger, look at the math. It doesn't make any sense. All right, so we know the mass of an electron, and if we sub it into this formula over here and we let the electron travel at the speed of light, well, we end up getting a c squared over c squared, which goes to 1. 1 subtract 1 gives you 0. The root of 0 gives you 0. And any number divided by 0, well, we'll just get out of control. All right, and you'll approach infinity for your calculations. And that can't make any sense. How can you have an infinite amount of energy to charge your cell phone? Right? You'll run out of juice before you even start charging. And even if you decide to slow it down by a bit, down to 99% of the speed of light, well, that still gives you a rather ridiculous number. All right, 3.1 megajoules, well, that's close to 1 kilowatt hour. And remember, a kilowatt hour is the amount of energy required to heat up or to even turn on your blow dryer for about 2 hours. All right, so look at all the heat that's released from there. And you're telling me that you need to release that much heat just to even start moving electrons so that you can charge your cell phone? It doesn't make any sense at all. Okay, where in reality, electrons, they travel really slowly. Now this animation is running way too fast. It should travel closer to the speed of, yeah, like that. Only a few millimeters per second, especially when you're only delivering 1 amp of current. All right. Okay, even velocity calculations get rather messy. All right. especially relative velocity. You might be used to this one where in grade 11, the velocity of an object relative to the ground is equal to the velocity of the object relative to the medium you're traveling at, plus the velocity of the medium relative to the ground. All right, so this formula is perfectly fine. Some textbooks use v of what is it, uv is equal to v of u plus yeah, something like that, v of v, some crazy notation like that. And here's another rendition of it right over here. All right, so yeah, that's the proper formula. So yeah, it looks crazy. Don't worry about it. It's highlighted in yellow just to emphasize to you that yes, there is a correct formula for what you're supposed to do with velocity. So if you're near the speed of light, you have to use this formula over here. But if you're traveling, at speeds that you can only accomplish here on Earth, physically yourself, then yeah, you can stick with the simplified formula. Other than that, that's it for today's lesson. Get crunching on your homework, and I'll catch you in the next episode.